The last big topic in chapter 15 is Lewis acids and bases. You know, it was called equilibrium of other reactions, but we knew acids and bases just had to sneak their way back in. So we've talked a lot about acids and bases, and we've really talked about kind of two different descriptions of it, the Arrhenius definition and the Brønsted-Lowry definition. So the Arrhenius definition is all about water, right? Acids make hydroniums in water, bases make hydroxide, very focused on water, and it's really limited then to aqueous solutions. But we use it to do things like, that's where we get like definitions and ideas about pH comes from the Arrhenius definition. And kind of all of those ideas are all about reactions with water. The Brønsted-Lowry definition then was a generalization of that to kind of describing that this idea of forming hydronium and hydroxide is all about transfers of H+. And so it's really important that Brønsted-Lowry definition lets us look beyond just kind of this aqueous limitation. So you can look at reactions that actually aren't even happening in water. But more importantly, you can look at reactions between, like, say, solutes in water. One of the really kind of important things about it is it also lets us kind of look at the reaction as a whole, right? The actual reaction, the actual changes, the interactions between two different molecules, not just I put this into a solution or put this into water. How does it affect the solution? Right? It lets us make predictions about changes in molecules and that kind of stuff. So it's a bit broader of a definition. So what if we could go even more generalized? One of the things about Arrhenius and Brønsted is it's limited to things with hydrogens in it. What about kind of these patterns of reactivity that could go large at a larger scale or a bigger idea? So everything, if we look at, say, a reaction of, say, hydrochloric acid reacting with water, where the hydrogen moves, reacts, we'd say that the hydrogen transfers over to the oxygen, right? All of our ideas about acid-base chemistry were all focused on the hydrogen. So what Lewis acids and bases is, it takes this same reaction, but instead of focusing on the hydrogen, we focus on the electrons, with the idea that electrons are actually the driving force of chemistry. So it's the same idea, but instead of saying the hydrogen transfers, instead of saying that the hydrogen transfers over to the oxygen, we say that the electrons from the oxygen form a bond with the hydrogen, okay, with the hydrogen atom. And so acid-base reactions, even all of the ones that we've talked about before, always involve the creation of a covalent bond where both electrons come from one of the molecules, right? The idea is we transfer an H+, right? These electrons that say were here in the bond, boom, stay on the chloride. The hydrogen leaves as an H+. It doesn't take any electrons with it. That's why what was, say, a lone pair on the oxygen becomes the bond in the hydronium ion. And so this is the idea of a Lewis acid, that really, yes, the H+ is a very common mediator, but really what's also kind of unique here, characteristic here, is the idea of forming a bond that's, say, donated, right? Both the electrons come from initially the water molecule that end up forming that bond. So this idea is Lewis acid bases. A Lewis acid is the molecule or the atom that is accepting those electrons, and the Lewis base is the electron donor. Lewis acids tend to be things like cations, or anything on the left of the periodic table. Lewis bases tend to be anions. You always have to have a lone pair. Lewis bases always have to have lone pairs. That's indicative of the fact that, those electrons donate into a bond. This type of bond that you form is called a coordinate covalent bond. Anytime where you have both electrons come from, say, one atom, non-coordinate covalent bonds, kind of true sharing covalent bonds would be where you, say, have one electron, you share two electrons and each one comes from, say, the two atoms that are joined in the bond. And so it usually corresponds to basically a lone pair becoming a shared pair. Here's an example where, say, the lone pair on this nitrogen donates in and becomes the bond between the nitrogen and the boron atom here. A lot of times in this Lewis acid-base chemistry, you form, say, a single product here. You don't just, say, break off a hydrogen atom. Oftentimes you see this here in acid-base chemistry, and we call these adducts, the molecules that form as a result of these coordinate covalent bonds. coordinate covalent bonds are not as stable as, say, full shared covalent bonds because you have this kind of donation. It's not an equal sharing. So these molecules, they still are molecules, but we call them adducts, which kind of corresponds to, signifies how they form. Transition metals are really common Lewis acids. Transition metals can form what are called complex ions. So we've kind of touched base about these a little bit in lab, but basically, if you think about, a cation is a really good acceptor of electrons, not very good donor. So that's why cations, especially transition metal cations, are always Lewis acids. They're very good Lewis acids because they're very positive. And basically what happens is this lone pair can come in and donate electrons to kind of share with the silver. And then you form this adduct, and this can actually happen multiple times. You'll note the silver is a pretty decent Lewis acid. It accepts all sorts of electrons. It says that there was a lone pair here from one ammonia and another lone pair from a separate ammonia. And overall, you make this large complex that would still be called an adduct, but does form here, kind of floats around as a single object. And so these do form. This is very common that Lewis transition metals are Lewis acids, and they react with anything that basically has a lone pair on it. So let's look at some reactions and identify the Lewis acid and Lewis base. I got ammonia reacting with water, BF3 reacting with NH3, and then copper cations reacting with water. All right, so we want to identify Lewis acid and Lewis base. So this Lewis description is a new one, right? It's a new kind of designation for acids and bases, but still is trying to accomplish the same thing. We're still trying to describe reactants in a reaction, to understand consistent patterns of reactivity. If we look at our first example, it's ammonia reacting with water to make ammonium and hydroxide. This is an acid-base type of reaction that we've seen previously. Lewis designations are looking to just basically describe more types of reactions, but they're still describing all the same types of reactions we've seen previously. Some sort of compound reacting with water to make hydroxide is the stereotypical base. Ammonia we've identified as a base. We've seen it react as base repeatedly, again and again, in a lot of different contexts. And so our description here should hopefully do the same thing. If a Lewis description classified ammonia in this reaction as not a base, we wouldn't be talking about it in this class because it wouldn't be useful. Right? We spent weeks talking about acids and bases. If we're going to come up with a new designation, it needs to describe all the same chemistry in the exact same way. It's just going to basically allow us to talk about a little more types of acids, some different types of acids that do slightly different, look a little different, let's do similar types of chemistry. So primed ammonia better be our base. So we kind of want to look at when we see a reaction, if we can classify it using our older methods, Arrhenius or Brunstad-Lowry, use those and kind of check that your Lewis answer is the same. But in general, if I want to come up with Lewis acids, we always want Lewis acid base. It's really a more molecular approach. We're recognizing the fact that ammonia looks like this, right? We can draw up the Lewis structure, the same Lewis. He came up with both Lewis structures and Lewis acid base. So hence the structures make it easy to see what's going on. So ammonia is NH3 with one lone pair on the nitrogen, water, H2O with the two lone pairs on the water. You will note we are forming ammonium. So the nitrogen is going to gain a bond with hydrogen. We can see it's not going to take any electrons because it's H+, so it's going to be this coordinate covalent bond. Those electrons donate in. Because the electrons start on the nitrogen, this is my base, and water, which is where the electrons are going in, is the acid. Same as we would have characterized for a Brunstad-Lowry or Arrhenius description that you make hydroxides. In the Arrhenius description, water, ammonia produces hydroxide, so it's a base. Ammonia takes an H+, so it's a base. Ammonia donates electrons, so it's a base. All of those are saying the same thing. Just how generalized or how generalizable is the definition. BF3 plus NH3 produces this F3B NH3 adduct. It looks like a little arrow's gone. So this case again, one of the things, ammonia we've said almost is always a base. You can still use those ideas. Ammonia still is going to function as a base probably, but let's draw the Lewis structures to make sure. B, F, 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 so boron trifluoride, and NH3. Okay. And we can see this kind of weird molecular formula here that's showing the N with an arrow explicitly into the B. What that corresponds to is that these electrons are going in and forming a bond, forming one of these coordinate covalent bonds. The two electrons start on the nitrogen, they become a shared pair, become a bond, that's a covalent bond, where the electrons are shared between those two atoms across, it's holding the molecules together into one adduct. And so, but we can see that donation, meaning that ammonia is the base. Again, consistently, whenever you see ammonia, the things that tended to be bases previously, still going to be bases. Boron is the acid. So this is one of our first kind of clues. Boron is a very strong Lewis acid, independent of what molecule it's in. Boron, strong Lewis acid. Especially, you'll notice it doesn't have a full octet. You'll note acids receive electrons, right? They accept electrons. Boron in this molecule only has 1, 2, 3 bonds. That's 6 total electrons. It's not a full octet. Very much would accept those extra electrons. Anything without a full, so beryllium also strong Lewis acid. Copper cation plus water. Water, we don't really know, go both ways, so let's write it out. Cu2 plus H. Okay, what happens here? Well, this idea, when we see over here the copper bonded to the waters like this is one of these complex ions. And what ends up happening is these lone pairs donate in. Okay? We don't know too much about these complex ions, what's going on. But one of the things we can know is that if you have a transition metal or a transition metal like copper, the transition metal cations, the Lewis acids. One of the things you can think about is Lewis acids, again, accept electrons. Cations tend to accept electrons. You may also remember previously we learned that cations cannot be bases. We were talking about Brunstad bases in that time. Still true here. Cations are going to be acids. Cations tend to be acids. Not all cations are acids, but transition metal cations, main group metals, so the P metals, aluminum, tin, everything that's on the right side of the transition metals, those are also Lewis acids. Sodium, potassium, the group 1A and 2A, the neutral cations, are still neutral. They don't behave as Lewis acids either. But this is going to be a Lewis acid. Copper cations are definitely Lewis acid. I forgot to actually write out the description. Acid and water is. So transition metal cations, always going to be your acid.
Participation 320, question 4. Identify the Lewis acid and Lewis base in each of the following reactions. I have two reactions, HCl aqueous and NH3 aqueous becomes NH4 plus aqueous and Cl minus aqueous. And then Al3 plus aqueous and 6H2O liquid becomes Al H2O6 3 plus aqueous. This is the fourth question on participation 320, due Friday, March 20th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the link, right below the document where these videos are posted. Again, identify the Lewis acid and Lewis base in each of the following reactions. Hydrochloric acid plus ammonia makes ammonium and chloride, and then aluminum cations and water makes an aluminum hexa-aqua complex. Okay, for another question on participation 320, I think there's one more video in this set. Yeah, one more video in this set. A little more Lewis acids and base with equilibrium. I'll see you there.